Okay, it's 4 p.m. I think we can start. So first of all, thank you very much for joining to this webinar. Today we are gonna, let's say, go into deep dive on the electric drives control and how to use and leverage virtual thermal sensing technology in order to enhance the performance of the electric drives application. So here we have the brief agenda of today. I will start talking and tell you more about Newton technology, so how to generate and deploy virtual thermal sensor, even if it will not be the focus of this webinar, but it will be the focus of the next chapter on let's say, the creation of this virtual thermal sensing technology. Today will be more oriented on how to use them, so on how to leverage the enhanced information in real time in closed loop control in order to improve the performance, the safety, and the efficiency of your electric drives. So let's start. Newton is a software company which is working at the forefront of physics AI software sensor solution. We have developed the first engineering platform named Twin Fabrica, which is meant to create and deploy virtual thermal sensor at scale. So basically, we have integrated a streamlined 6-step unified methodology where you can import your geometry, set your material properties, you can import your finite element simulation analysis, you can make multi-physics simulation, you can get your ROM, so your reduced order model, thanks to the model order reduction libraries integrated in this software. You can import your real data coming from the field or coming from the, let's say, the entire engineering process of your electric motor production or your software or your traction inverter, etc., etc. And then you can also empower your reduced order model with AI in order to, let's say, improve the accuracy and the reliability of your system, such that once you are satisfied with your requirements for production, you can export the final firmware to be plug and played inside your software architecture. So, as I mentioned, I will not focus today on how to create, deploy, and validate virtual thermal sensor, but we will focus more on how to use them and extract value from them. So basically, the first comparison that we are going to analyze together is the kind of sensor feedback respect to the state of the art of hardware. So today on the electric drive application, once you have to control your electric machine and your traction inverter, basically you have at your disposal two main temperatures. One is the temperature in the stator winding when you're lucky enough that, let's say, you can place them, because, for example, if it is not easy or if you jeopardize the kind of speed for the installation in production, this kind of sensor usually they are in some cases placed into, let's say, the stator iron. The other main temperature that you have, it's the one provided by the supplier of the power module that you're integrating your traction inverter. So you have the temperature near to the semiconductor junction, but you know, it's let's say it's not an accurate state-of-the-art sensor feedback for giving you the right accuracy information on the junction temperature. So let's see which are the main functionalities, using the virtual thermal sensing technology. Basically, once you have this technology at your disposal, what you can do, you don't have any more sensor placement limitation, because these virtual sensors, they are model based. So basically you have the geometry enhanced in your sensing technology, and you can place sensor wherever you want. So you don't have anymore the, let's say, engineering constraints. You can place a sensor also in rotating parts, like in the magnets or in the bearings. You can place sensor in all the semiconductor junctions of the dies of your power module. And this is, let's say, the first functionality, the first advanced functionality respect to the state of the art. The second one, since still they are model based, You can ask to your model what will be the future behavior, the future thermal behavior respect to, let's say, certain conditions. So basically, you can predict the future on a selected predetermined horizon windows length, and you can apply what-if scenarios, you can apply model predictive control, and we will see in a while how useful it is, for example, for controlling the permanent magnet temperature. As last, let's say, advanced functionality that you have is the granularity. So basically, in the state of the art, you have at your disposal a thermocouple or an NTC in the electric machine or traction inverter, which is giving you the information of the temperature in one point. But we know that for high current density application, the gradient of temperature, of course, is not uniform, and the temperature in a single point is not enough to identify the hotspot. So on the contrary, on the right-hand side, we have the virtual thermal sensor, let's say, functionality where you can exploit the granular insight information, like having an IR camera running in real time in your microcontroller unit, which is calculating which is the hotspot, which is the hottest surface in your system, and you can use that kind of information in closed loop control. So now let's see together how to use this enhanced sensor feedback information. And we will start first with the inverter derating control. So in this slide here, I will start briefly describing the two PI control loops that there are here used for controlling the junction temperature in the system. In the state of the art and the in the VTS case, so in the virtual thermal sensor case, in this case, the control algorithm is completely identical. The schematic doesn't change, it's the same. As you can notice, there is a first PI control loop, which is derating the switching frequency until a certain amount of, until its lower limit, that in this case is fixed to 85% of the nominal switching frequency. And once this control loop reaches its lower bound, it is triggering a second PI controller, which is then derating the module of the current. So basically, with this control schematic, what you are doing, you're acting on the switching frequency and on the current in order to reduce the losses due to switching frequency and due to conduction in order to control the junction temperature until its safety limit. So what does it change here? What it changes, it's the feedback. So on the left-hand side, so in the case of state-of-the-art, usually you have at your disposal an NTC measurement plus a correlation model, in the best case a dynamic correlation model like a thermal network. And since you know that these models, usually they are not accurate enough, at least not in all the operating condition of your system, you are applying a safety margin of 25 Celsius degree, which, let's say, are limiting the functional burden of the power module itself, because in the case of silicon carbide technology, as the example that we will see later, the temperature limit is 175 Celsius degrees. So if you apply a 25 Celsius degree of safety margin, you're limiting the junction temperature to be controlled under 150. And we will see later how these can compromise the performance, mostly in the acceleration. So the second control strategy that we are going to analyze together today is the enhanced MTPA and field weakening dynamic trajectory calculation. MTPA stands for max torque per ampere, and field weakening or flux weakening, let's say, is the trajectory where you're applying the limit in the voltage. So on the state of the art, usually you predefine offline these current trajectory. So based on the torque reference, the speed, the DC bus voltage, and the current limit, there are these, let's say, offline model or lookup tables that you define with using, for example, electromagnetic simulation. So you take into account about the saturation effect, etc., etc. But you don't take into account about the magnetic flux. So the permanent magnet flux actually is changing with the temperature, But you can't take into account about this because you don't have it in real time, this information. You can't basically measure the temperature in the rotor. So with virtual thermal sensing technology, instead, you can place a virtual sensor, a specific one, so a real-time BTS, that is describing in real time, that is estimating, not in this case the hot spot, but the volume average temperature of the permanent magnet. And so you can use this to calculate in real time the dynamic change of the magnetic flux, which can be used to optimize the real trajectory of MTPA and field weakening in your control. What does it mean? It means that you can enhance the efficiency of your electric drives. So to move on with the third, I would say, control derating strategy, so the one regarding the motor, here we have two main bottlenecks in the electrical machines. One is on the insulation winding. It's well known that statistically the main cause of fault for electrical machine is the degradation on the insulation winding. So it's a quite critical temperature. You want to be sure that you can monitor the temperature of your insulation winding below certain level that is defining the insulation class of your electrical machine. And so basically to do that, you use a simple PI controller, which is derating the current. And in this case, in the case of state-of-the-art, since you know that a single point of measurement doesn't match, of course, the hotspot in your real system, you're applying a safety margin, in this case of 20 Celsius degree. So if the insulation class of that this material that you have chosen during the design phase can even support, let's say, stay continuously to 180 Celsius degree without jeopardizing the lifetime of your electrical machine. Here you're applying a 20 Celsius degree of safety margin, so you're limiting the temperature measured with your NTC or thermocouple to 160, acting on the derating of the current itself. Instead, on the right-hand side with the virtual thermal sensor, you have much more information, because instead of having just a single point of measurement, you can have a granular information of the end windings, of the core windings of the insulation itself. So you can be much more precise, and you can lower your safety margin to 0 in the best case. So you can apply a temperature insulation limit of 180 Celsius degree. We'll see in a while what does it mean in this case in terms of torque performance, nominal torque performance, as well as rated speed increase. Here we have a second control loop that is highlighted here, basically, which it is very important to monitor in this case and control the magnet temperature, which is the second, let's say, bottleneck for our electrical machine, because it's directly tied with the efficiency. So if you want to have the chance to control the magnet temperature in this case, you need to use this control loop control. So basically the architecture here, you have a PI which is derating the current in order to limit the insulation temperature of your winding, and on cascade, you also are limiting further if you reach the maximum temperature limit in your current, in your magnet. So basically, even if you have the chance to measure with the sensor somehow the temperature in the magnet, in the hot spot of the magnets, in order to avoid local demagnetization phenomena, it's not enough, because the rotor dynamic is very, very slower than the dynamic of the current. So if you want to have the chance to control it, avoiding the so-called theoretical effect of this control loop, you need to use a prediction that is 100 times faster than real time in order to have comparable dynamics and in order to control smoothly the temperature magnet limit until it's, let's say, operating condition. We will also see in a while this kind of effect and why it is so important. So magnet temperature is, as I mentioned, directly tied to the efficiency preservation of your machine. And here we can go on deep dive. Basically, when you are designing your machine, you are selecting a certain rare earth, so you have certain magnets. You can ask to your supplier this kind of magnetic curves, where you can see on the green line you have the operating line of the magnet. In violet, you have the, let's say, permanent magnetic behavior. So here, the operating point of your machine is defined between the intersection between this green light and the violet one for different, as you can observe here, temperatures of your magnet. So basically, you calculate which is the maximum operating temperature for your electrical machine, and in particular for the rotor magnet of your electrical machine, with the last, let's say, operating point that intersect the violet curves until this knee, the so-called knee. If we, let's say, heat up too much the magnet, and as in this case on the left hand side, we stay below the knee, as in the case of 120 Celsius degree. The operating point is this yellow point here. We are below the knee, and we have a irreversible loss of magnetic strength. So basically, if we cool down again our permanent magnet, so our motor, the new operating point will not be anymore the blue line here, but it would be this new yellow dot where you have a magnetic strength, let's say, that is lost on an irreversible way. We can also try to do, let's say, brief calculation, just multiplying B by H, and you can verify that you have a 40% of lost of magnetic strength. This is, let's say, translated on a loss of efficiency. The ratio is not 1:1. I mean, even if you lose 40% of magnetic strength, it's not said that you are losing 40% of efficiency, because you have less back EMF, basically. So you need less voltage in this case. So the ratio between the mechanical power and the electrical power is not directly related with this loss of magnetic strength, but it's, however, directly tied with the efficiency of your machine. So if you don't control, if you don't monitor the magnet temperature, you risk to jeopardize the efficiency of your electric motor. That's the reason why it's so important to control it. So let's see some results. So let's analyze what does it mean to reduce the safety margin. And in particular, the first test here, it's a speed control test. So our motor was controlled to 6,000 RPM, and there was another motor that was basically holding the torque, so braking, and with a torque load of 300 Newton meter. As you can see, for the first 600 seconds in this case, we can hold the speed with that torque load, but of course, we are asking certain current, and so our motor is heating up, as can be observed here. And once the state of the art reaches the 160 Celsius degree, the effect of this control loop, of course, is derating the current. So in this case, we can't anymore have the 300 Newton meter at to fight with the other motor, and so we lose the control. Why is this test? This point is very close to the base speed, so it's a very interesting operating point for our machine, and we can see how much we can improve it, because using instead virtual thermal sensing technology, so if we lower to zero this safety margin, so if we use the 180 Celsius degree, we can have an increase of 8.3% in the rate of speed without losing the control. So in this case, using VTS control, basically you can hold continuously the speed without any problem with this 300 Newton meter. So, and that was the effect on the motor winding temperature. So if you reduce this 20 Celsius degree of safety margin. Now, let's focus more on the peak torque duration test. So basically, If there are any questions, sorry for this. Let's stop 1 second. If there are any questions, please continue to write in the chat, and once I will finish, I will try to answer and do my best to answer your question. So let's continue. For the acceleration performance, basically we are asking for the peak torque in the system. So we are asking for the peak current, and we are talking about a few seconds. So the acceleration performance, we are not talking about very long period, but very short period. And in few seconds, the temperature of the electric machine, let's say, is not affected by, let's say, huge variation. On the contrary, the power module, so in this case, the inverter, is the bottleneck, because the dynamic of the temperature in the power module are very fast, and in a few seconds you can really raise your temperature until very high limits. So here we can clearly see the effect of the 25 Celsius degree in safety margin. Basically, if you remember, the control strategy here was completely identical. It was the same. So what does it change? Is just the safety margin of 25 Celsius degree. And using, so lowering until to 0, so using the full functional burden of our power module until 175, basically, we clearly see the good effect of this control loop, where the switching frequency is derated first from 100 to 85% of its nominal value, and then it's triggering the second control loop, which is then lowering the conduction losses and so the current. So basically, this control allows you to increase the duration of the peak current of your system. And the effect is clearly visible here using VTS, because after 2.5 seconds, we reach the 175, and then you can, let's say, control the junction temperature, but holding still the peak torque, and you will start decreasing the current just when you reach the lower bound of the switching frequency. So in this case, that 25 Celsius degree of safety margin really is compromising the performance of the peak torque duration, because without that, so lowering that, you can have a 5-time increase of this peak torque duration. So, and it is quite, let's say, important KPI for acceleration performance, mostly for the application like motorsport. So if we continue with the test, so if we continue to ask the, let's say, maximum torque to our system, and with the other motor, let's say, hold lower speed, so 1000 RPM as low speed, 1000 RPM as in this case, we can really explore let's say, a full operating point and temperature limits defined by our derating strategies, as can be observed for the next second. So from 0 to 60, we can obtain increased current in our system, and so increased torque in our steam system, thanks to the 25 Celsius safety margin here that has been reduced in the power module inverter control derating. And then once we reach the 180, in this case, in the motor winding temperature, of course, there will be the second control loop here that is acting on the current, and so it's limiting the torque, basically, because current and torque are proportional one to each other, until you reach the steady state. So you can control safely to 180 and 175 the motor winding and the die of the junction of the inverter. Here we can see a clear effect in the max torque and also in the nominal torque. And this second one, the 16%, when everything is steady state, so you don't have variation on temperature because it is controlled to its limit of 180 in the insulation. You don't have variation on the torque, you don't have variation of the speed, so everything is in steady state. In this case, we have an increase of 16% in the nominal torque. So this is true, but it's true for this operating point. It's not true for the entire operating speed range of the system. That will be explored and analyzed in a moment. We will see together a full simulation exploring the full range of speed, such that we can appreciate the two areas defined by the torque with the state-of-the-art or with virtual thermal sensing technology. Before that, we have the last test done here that was quite important to highlight how important is to monitor the temperature in the magnet. So basically in the on-off application where you don't have, let's say, a priori information on the mission profile, so you don't have mission profiles that are already determined, so you don't know nothing basically about the thermal behavior of the rotor. So you don't know nothing about when you on again your system, what will be the rotor temperature, so the magnet temperature. It's fundamental to have a virtual thermal sensor there that you can use in order to control if you want to avoid the demagnetization. Here is clear how motor magnet temperature and motor winding temperature, they have different dynamics in this case. So even if your winding temperature has cooled down, it's not said that your magnet temperature has cooled down enough such that you can restart with your operating condition. And this is the case. So without knowing this, your control is completely blind. And even if you're using the safety margin, you can't avoid this irreversible demagnetization. And so you can't avoid the loss of the efficiency. Instead, if you use this second control loop, so if you can predict the temperature 100 times faster than real time in your magnet, you have the chance to calculate which will be the current reference such that in steady state you do not, you can control the system to a safety limit that in this case, the operating limit, if you remember, was 100 Celsius degree. And this is exactly what is happening here. After the, let's say, estimation of the virtual thermal sensor in real time, it's getting closer to 100 Celsius degree. That control loop, it's acting and it's calculating super fast, which will be the current level such that in steady state, and here you can see the first transient, you can control the temperature in the magnet monitor below the 100 Celsius degree. So basically, to recap which kind of added value you can, let's say, enable thanks to the virtual sensing technology, you can basically increase the rated speed of your electric drives. Of course, this number, once again, they are calculated on a specific case, on a specific operating condition, and in the best case where we are lowering to zero the safety margin. Not said that you have to lower them to zero. Maybe you can lower them of 50% or 60%, and still you can have a very huge margin in the increased performance. So basically, with the same identical hardware, you can have more performance if you use this kind of control, or with let's say same performance requirement, if you use this control, you can basically design cheaper, so a smaller electrical motor, or you can use a cheaper, so smaller power modules. So just to recap, you can increase the rated speed of your electric drives. You can extend the peak torque duration. The max torque and nominal torque also can be increased. But most importantly, as I always define, you can increase the state of function. So basically, you can maximize the performance of your system, but in a safety way. So without jeopardizing the lifetime, the remaining useful life of your electric motors. And this is done thanks to the fact that you can control also magnet temperature, avoided the magnetization effect. So now we can see together before the Q&A session a full, let's say, simulation here. Done on Simulink. So basically where in the meanwhile, I also run the simulation. So basically here we have state-of-the-art control and virtual thermal sensor control. We can look inside here. To perform this simulation, we are using two digital twins. So one of the electrical motors, so basically the electromagnetic and thermal behavior here is executed in real time. The other one on the power modules. And here on these three blocks, you have the MTPA and field weakening trajectories that in this case we are using the temperature magnet in the volume average of the magnet of the electric motor. We have the derating strategies. So first, acting with the inverter derating, which has a highest priority respect to the motor derating, and then this reference is fed is entering as input in the motor derating that in this case is using, as you can see here, a model faster than real time in order to control also the magnet temperature. So, and here in this block, we have a current control that basically is following the reference and is calculating the duty cycles for the traction inverter. Now we can see here we are asking for a certain ramp of speed from 0 to its maximum limit. So basically now it has just achieved the maximum operational limit speed for the system. And we can see together how the two electric drives that are running in parallel with the same models, but with different, let's say, control strategy architectures where they are differing and with different, let's say, limits, operational limits for the safety margins. So here we can see in green line and orange line, you have the IQ and ID current using BTS control, while in blue and yellow you can see IQ and ID current using the state of the art. As can be noticed, here we have the peak torque, then we are still on MTPA until the second 55, more or less. Here we enter in the field weakening control, where basically if we go back here, we are running from the MTPA point automatically to the field weakening, thanks to our control strategies. Then you can see also the effect on the torque. So as demonstrated in the slide, here you can see clearly the effect in the peak torque duration that can be enhanced using virtual thermal sensors, so the orange line. Instead, in blue, we have the torque using the state of the art. We have also two different torque level for the fact that in the virtual thermal sensor case, we are also using the real-time volume average temperature of the magnet to calculate the real MTPA trajectory. So the efficiency of our electric drives is improved. And then, of course, here we are on a steady state. Here we are on MTPA until more or less 60 seconds when you have the field weakening, and you can see the area of the, let's say, orange torque here is much more, let's say, huger than the area of the blue one that is the state of the art. These can be also, let's say, seen basically multiplying the torque by the speed. So you have the same, you can see the effect on the power. If you integrate, you have also the energy. And if you also see the difference, you have how many kWh you can have, you can increase with the using BTS technology respect to the state of the art in 200 seconds. So regarding the temperatures, let's see if they are all satisfied. So here you can also observe the sensors, the virtual sensors in the head winding and in the rotor temperatures. So basically, here it's clear how you can control the highest, let's say, winding temperature to 180 Celsius degree. You can also see the clear effect of the cooling, so inlet and outlet. So basically the pink, the red line here is the end winding where the coolant is entering in the machine, as can be observed here. We have the same also in the other But now, as you can observe, the temperature in the winding is controlled to 160 and not anymore to 180. So the safety margins that we have mentioned during the presentation. And then I would like also to see with you which is the effect of the inverted derating. So basically, here we have the virtual thermal sensor that is basically predicting the temperature dynamics of E1, E2, E3, etc. These are virtual thermal sensor placed in the die of the junction, where we have also the NTC measurement that has a clear different, let's say, gradient temperature for sure. And you can see how the control can identify which is the maximum temperature of the system to be controlled below 170 Celsius degree, as in this case. This is not the, let's say, real dynamic of the inverter. It is the, let's say, the main one, the fundamental one. So you don't see the swing on this model, but in the real traction inverter model coming from the digital twin, yes, you can see. So here you can see also the swing effect of the electric period of the current. In fact, at the very first instance, when the speed is very low, basically also the frequency of the current is very low, so the period is long, and that's the reason why the swing temperature in the junction, they are more amplified, while with the speed that it's increasing, of course, this kind of effect is not present anymore. And in fact, when you arrive more or less at the rated speed, you have the reduced swing temperature. So in this case, we are not using this kind of feedback in our control, even if, as you can see with the digital twin, it can be appreciated. But we are not using it because it's much more difficult to control this kind of oscillation instead of having the fundamental, let's say, dynamic of the traction inverter to be controlled. So basically, this is almost all. Hopefully that it was clear enough. I know that there was a lot of information, but remember, you will have the, let's say, the full material, so all the presentation and also the recording. Now we have time to, let's say, try to review some of your questions and I do my best in order to answer them. Okay, just 1 second. Okay, so a virtual sensor has not only the added value to estimate the temperature in otherwise unreachable points, but also to predict this temperature much faster than real time. Okay, is this would be available? Okay, basically to answer this question, the virtual thermal sensor at the end, it's a model. So it's a state space model. We will have a deep dive session in the next chapter of our webinars, where we will see together how to create a virtual thermal sensor from scratch. So from the very beginning, from high fidelity models until the final firmware, to be implemented in the microcontroller, where usually the real sensor are read, and so where the virtual sensor are executed. But yes, since it is a model, basically you can predict the future horizon simply changing the integration time step of this state space model. So if you play basically on the integration time step of the state space model defining the virtual thermal sensor, and you play in which task of the microcontroller you will implement the virtual thermal sensor, and so where you are integrating the model, basically you can obtain the kind of horizon length that you would like to use for your electric drives application. So for the real example that we have just mentioned, how did I get a model that is 100 times faster than real time? Simply because the integration time step of the state space model that I have used was 100 times, let's say, huger than the period of the microcontroller where it was executed in real time, and that for sure it's helping you to give you to give you fast prediction. So how do you ensure your VTS model is correct for all motor which are not all exactly the same? Very nice question. And this also will be part of the next webinar, but to provide you a preliminary answer, we as Newton define, we provide engineering software platform, as I mentioned before, to Infabrica. And this engineering software platform allows you to test in your experimental environment the kind of fidelity of your virtual thermal sensor. So basically you have the chance to validate the goodness, the accuracy, and the reliability until you are satisfied for your production requirements. So my answer would be you have the chance to test them. You have the chance to test them on different conditions, on different testing. You have the chance to test them how they react to manufacturing errors, how they react if you change, for example, the supplier of the iron, etc., etc., etc. But if you change drastically, of course, the geometry and the motor typology, the motor topology, of course, you need to, let's say, have a different model, and so different virtual thermal sensor. Okay, just make sure I understand correctly. Is it really a different control strategy between state-of-the-art and VTS? My understanding is that it's the same control strategy, but with more confidence in the temperature measurement estimation, so there is no need to make a safety margin. Is my understanding correct? Yes, basically, part of the control strategy, they are identical, as I mentioned before. What is changing is the sensor feedback. So basically the control loop feedback is changing. It's not coming from a real sensor, but is coming from a virtual one. And since the accuracy is higher, you can lower the safety margin, yes. In other times, so in other, let's say, point of the presentation instead, since you have this enhanced information, sometimes you can't have, for example, the magnet temperature estimation in real time, or you can't have the rotor measurement in real time. And that's the reason why, in that case, the control strategies was even different, because you have a cascade PI controller loop, which in the case of the state of the art, you don't have. So basically, if I go back to presentation here, this control strategy is basically different because here you have a cascade of PI controllers in order to derate the current that here in the state of the art you don't have. Okay, let's go on. Okay, can BTS method be used for safety relevant temperature measures? Very nice question. Of course. So virtual thermal sensor can also be used on top on the, let's say, main functional testing. Let's say normative is not so clear. Of course, you can't remove the real sensor from the functional safety, but you can complement the real sensor measurement feedback with the virtual thermal sensor one in order to even improve the safety of your system. How can you guarantee the accuracy of the virtual sensor based on partial data of the real motor / drive? Yeah, as I mentioned before, it is customer dependent. I mean, we don't choose for the customer the accuracy. It's the customer that set its highest standard for accuracy. So if you have a very good electric drive test bench and you can test your electric motor on a full operating condition, so exploring all the speed, all the torques, all the currents, different cooling condition, different flow rates of the coolant, different temperature of the coolant, you have also the chance, and you're oversensing during the engineering phase your electric motor or your power converter. you have really the chance to validate and to measure the level of generalization and reliability of your virtual thermal sensor. So once you are satisfied with that and you are ready for production, you go in production, basically. One question, how you ever done any validation of the signals calculated by the digital twin? Okay, very nice question. I have here an example. So basically for the power module, one thing that you can do, you can test them, basically removing the cover. You can use an IR camera measurement. You can basically record the dynamics of the temperature on each single die, and using this kind of testing, you can validate your virtual thermal sensor under all the operating conditions. For the electric motors, instead, if you want to validate also the magnet temperature, what you can do, you can drill the rotor axially and radially. You can place different thermocouples inside. You can use a wireless transducer sensor in order to, let's say, use that feedback for the validation and for the generalization of your model. Hello, is the VTS estimation validated through all the motor operating points through test data comparison? Yes, usually. With what accuracy does the VTS estimate the magnet temperature? Very nice question. Basically, in the automotive space, the target of accuracy that our customer they require is plus minus 5 Kelvin or 5 Celsius degrees. It's the same. It's an error. In all the operating conditions, not just steady state, but also during the transients. In other cases, this kind of, let's say, constraints in the accuracy is even lower. We have also customers that they ask for 2 Celsius degree, 2.5 Celsius degree in all the operating conditions. So basically it is customer dependent, there is not, let's say, any kind of normative here that can force you to have a certain accuracy, but based on your accuracy, you can take your decision on how much you can reduce the safety margin of your electric drives. As I mentioned at the very, not at the very beginning, but before during the presentation, the best case is lower to 0, the safety margin, but maybe this is not always possible. So even if you can lower the safety margin of 50%, because today they are really, really huge, you can still gain a lot of performance in your system. Okay. Is there IRF means the phase RMS? It's the module. So usually the current reference to be modulated is the module. So it's the square root of IQ square plus ID square, basically. Can BTS method be used for safety relevant temperature measurements? Of course. How can you guarantee the accuracy? I have already answered this, so good. It seems that we have, let's say, answered many of your questions. Time is almost finished. What if the magnets become dirty/dusty over the lifetime of the application? How will the virtual sensor maintain accuracy? Very nice question. Basically, all the phenomena regarding aging, regarding anomalies, etc., they can be somehow mitigated thanks to virtual sensing technology, because remember that you will always have a real sensor in the system itself. So, and virtual thermal sensor at the end is a model, and one of the input of this model is the real sensor feedback coming from, for example, the NTC on the stator or the NTC in the power module. So you have the chance to integrate with your virtual sensing technology also state observer. Actually, the state observer is intrinsic integrated inside virtual sensing technology. It will be, let's say, demonstrated on the next chapter. And this kind of functionality really helps to mitigate this kind of, let's say, uncertainties in the system. Of course, it's not magic. So if the system is, let's say, has a highest degree of observability, and your model is very robust, the state observer can really do a good job in doing that. So in mitigating this kind of uncertainties, it's not always the case. But we will for sure in the next chapter we will deep dive on how to create virtual thermal sensor on from the very beginning. How to validate them, how to use them, we have already seen, but how to integrate them in the microcontroller units, which is another very important challenge. Remember that this is a physics AI model that must be executed on very short task of the microcontroller. So the one of for example, 1 millisecond or 10 millisecond task of the microcontroller. So a model must be, yes, light and accurate. And this is the main challenges. And that's why Twin Fabrica is the first engineering software platform that can do that. So I think that we have managed to answer mostly all of your questions. And I will personally thank you to, let's say, follow this webinar. Hopefully it was, let's say, helpful for you. I remember we will deliver the presentation, the recording, so you will have everything. And if you have any further question or you would like to have a trial or a demo about Twin Fabric and our technology, feel free to reach us. Thank you very much and enjoy your evening and day. Bye-bye.